until now. I think we'll just start right at 2. So as I was leaving yesterday, I got a question by looking at or introducing self-organization. Aren't you just doing exactly what you said you weren't going to do, and that wasn't important and was maybe impossible? That is to find the golden trick, the golden key to unlock intelligence and enable us to do AI properly. So I thought about that a little bit, and I finally came to the conclusion as I was walking over here with the shortest answer I could possibly find to that. We're just getting started. So this is one of a long list of things that I will claim to be a necessary but not sufficient ingredient to achieve AGI. And of course, as soon as you hear that, it sounds pretty believable, doesn't it? I mean, it's kind of hard to buy the argument, frankly, at least to me, that there is such a thing as a neat trick. And all we have to do is just search, search, search. And you know, I think if you look back on science, you know, Newton's theory of gravity and Einstein's theory of relativity, these are not neat tricks. It took 2,000 years to get to that point. And Einstein said that numerous times, that he was standing on the shoulders of giants. There's not a chance in hell that he could have come up with that 100 years earlier. And so it's not really that we're just looking, and someone may get lucky and just find it. It being something like the algorithm that explains intelligence. It just doesn't sound right to me. Now, it could be that it's a small set of things. Ultimately, once we've sort of built messy versions and then honed them down and then distilled the principles and the essence, and, you know, after 1 or 2 decades of writing textbooks again and again and polishing and you know, focusing it down, of course, then it's going to start to look like, oh, it's not a big list of things, and you know, really, if it really boils down to it, you know, it's just a handful or maybe a couple of dozen things that really were new in the last 20, 30 years or something like that. So yeah, okay, that might happen, but I really don't think we're at the point where there's only one remaining thing to be figured out, and as soon as you insert it into whatever exists now, you have it. So that was my elaborated version of the very shortest answer I could find. So we're just going to scratch the surface on what myself and my collaborators in the HumanOps project, which was an EU-funded project that finished last summer, 3.5-year project, developed with the requirements that I listed to you in the end of the first session as the top-level guiding requirements. And then, of course, as I presented yesterday, there are some more requirements that we partially derived and partially had some hunch about having to actually work under. And I'm not going to be so explicit in continuing on pulling out requirements. I think it's going to become a task for the next few years to actually, for us to really separate out what could be, what's a good idea to list as requirements versus what's a good idea to list as, you know, here are some new ideas, etc. This will get sorted out as we write more papers on the results of that project. Unlike many big research projects, this one had 6 partners in 5 countries. We didn't really publish that much about the results of the project as we went along, because we had a hunch that because of the breadth that we were taking, the broad view, we would be better off holding off till after the project to really start to write the results up into publications. There have been a couple, and I will tell you about some of these today, but really all the major publications remain to be done, and so this is why there isn't a lot of publications on as part of your readings now on the HumanOps project results. The architecture we developed in that project got the name AERA, and also if you Google for that you won't find too much yet, and the best way to know what this is about is to pay attention to the remaining sessions that I have and my colleague Eric Nivell, who will join us on Wednesday. So on Wednesday we'll have the full day, and we'll go in fairly, as deep detail as we possibly can in that short a period without losing everyone. I'm sure we will lose some people. Some people may not be able to follow because, well, to actually grasp it fully, you have to have a fairly wide range of backgrounds and also be relatively trained at the present in thinking about them. So, yes, we're going to go slower than we did last summer school that we did in Reykjavik, because we felt that was somewhat suboptimal. After talking to the students after those sessions, our feeling was that we didn't do a good enough job of conveying the ideas. So we're going to go slower, and we took out some of the hands-on stuff that we had in that, because we thought, we could use that time better. So AERA is implemented, and it's software. It runs if you know how to run it, but we haven't had any time to really do tutorials or documentation, proper documentation that works for anyone but ourselves. So it really is an early stage here. I will show you some videos of that, of the results, what you can do with that, and we'll do that on Monday. And we'll show you some running examples. But really, what we're more interested in is conveying the ideas that led us to this system, and how we think it fits into the current landscape of AGI. Today, I will probably not run all the way to 5 o'clock. We'll probably break sooner. We'll see, maybe as early as 4. We'll see how fast we go. I saw at least one comment on the wiki, so we'll take that one. If you do some more in the break, we can do those as well. Okay, I think that's all I wanted to say up front. So, we're talking about autonomy. We're talking about attention and situatedness. These are really 3 concepts that we're going to be looking at today. You've heard them all before, of course. This is the origin of the word independence or freedom. The autonomy of the individual. This is from a dictionary. The condition of being autonomous, of self-government, self-governing. We become socially independent from our parents at certain ages, depending on the country. Typically, it's 18. I don't know what it's in China. What is it in China? Are you a fully autonomous citizen at 18 in China, or is it earlier? Or 16? Yeah, so you mature quicker than we do. We're just more immature, I guess. What type of autonomy are we talking about? Obviously, we can talk about all sorts of autonomy, freedom from various things, etc. We'll be mostly concerned with operational autonomy and autonomy of control. I will not talk too much about what we call existential autonomy, which is really what you could consider animals to be, or even at least a grown-up human will survive without a society if they get enough food and sleep and so on. But a human baby will not survive without at least one parent in the wild. There are species, of course, where the individual is just completely existentially autonomous at birth. And they just say goodbye, there's no concept of parenting, etc. And that's what we mean by existential autonomy. But we're really more talking about autonomy of control, that's operational autonomy, as well as goal autonomy, which isn't really a common term. You don't see that a lot, probably maybe not at all. I don't know. It's a concept we have recently started to use because in our systems, when I say we, my group research team, we consider the management of goals a critical part, the creation and management of goals a critical part of achieving AGI. And so we think that our approach is that the system must have autonomy on its goal system, goal mechanism. In the literature, you have various definitions. This is one from my colleague and collaborator in Spain. You've got a system, you've got a task, and you've got a context. System S is autonomous if it can fulfill task T in context C. However, the task and the context is defined. This is of course way too simple because if you think about it, how did this task come about? For AGIs, a refrigerator could be said to be autonomous because it can keep the interior temperature at a specific. This is kind of the lowest common denominator of definitions of autonomy. One of the things we'd have to ask ourselves is, where does this task come from? Did it come from the designer of the system? If so, then yes, you could say even a thermostat is autonomous. That's like the lowest end of the spectrum of autonomy. But if the system itself realized that this task was needed and then created this task for itself and then completed it as part of a bigger set of things that it wanted to achieve based on a goal of some sort, then you're stepping up in the ladder of autonomy. And I'll give you some examples in a bit. Why are we interested in autonomy? Why am I spending time on it here? Well, really, it's the same reason for AGI, and frankly, I have a hard time imagining how you could separate autonomy from AGIs. Because the further along the spectrum from a rock to an AGI you go, the more you realize the need for some sort or various kinds of autonomy, in fact. So autonomy is really a key factor. Now, researchers will, of course, I guess one of the reasons autonomy isn't too much talked about in AI or AGI circles is because it is talked about, don't get me wrong, but it's not, a central thing and it's not a frequent discussion topic. Probably because researchers typically build things in their labs that are meant to sit on a desk or in a corner and be probed at and tried and tested and modified and so on. They're not engineered entities that are put on a shelf in a store or let go in the wild. For that you have engineers, and the engineers will use principles that have been around for 20, 30 years that are tried and tested to do those things. What you have in the labs are, very sort of fragile things. You have code that breaks a lot, etc. So for example, robustness is a real determinant, a really important determinant of autonomy. And robustness is also not something that people do a lot in their labs, because for that you need all of the system to be running all the time, and to do that you need to write your code properly and or use really old technology. So to take an example, NASA does not send anything into outer space that hasn't been around for 20 years. So how can space technology be cutting edge? Well, it can't. It's not cutting edge if you look at all of the technology available. Space technology is cutting edge in space. But it's really 20-year-old technology at least, because they have to have trained engineers that between the ages of 15 and 35 or whatever were actually taught to use it and know it like the back of their hand. So robustness is also not something that enters into the minds of researchers a lot for this reason. But obviously there are some exceptions, like IBM's Autonomic Computing Initiative, which, well, we have examples of systems that we would love to have up and running and not have to be maintained, like network servers and routers and so on. If you have to reboot your router in your home at least once a week, like I do, it's a bit annoying. It's this little piece of varies in sizes, but it's a very small piece. It's been around forever. And why is it so fragile that at least once a week or so you have to reboot it? It's very strange. So robustness is hard to achieve, and also it doesn't really enter too much into the lab. And for the same reason, autonomy, robustness is a requirement for autonomy in some sense. Okay. So ways of thinking about whether a system is autonomous, doing something or not, is dependent, of course, on the environment, whether it involves some learning. We could have that list much longer. Does it involve creativity? Or does it require invention, etc.? But even just simple things like you get a new office assistant and you want them to just start working and be efficient. Well, if they're moving from Iceland to China and they haven't really been in this environment, it may take them a month to really get the hang of things, how they're done here. That's why you don't have software doing that kind of stuff, or robots, because it requires human ingenuity. It requires someone to be motivated to actually learn or unlearn what they did, how they did it before. So the less you have to specify a task that needs to be done, and yet the system can achieve it, the more autonomous the system is, at least with regard to that task. The more general the task is, also the more autonomous the system must be conceived to be. So if the system needs to change itself to be able to do the job, for example, well, I'm going to go mountain climbing and I'm really out of shape, so I'm going to go to the gym for 2 months every other day and to prepare. Now that's the kind of autonomy that we obviously don't have in machines yet. And as I mentioned before, it's hard to separate out autonomy from intelligence, really. You can think of them as two sides of the same coin. So this is how we see it. Typically, you will have underspecified tasks. No one wants to have to specify a task like we do. Imagine if for everything that you wanted to delegate to someone or something, you had to write a program in BASIC. That would be hell on earth, at least in my world. You'd have way too many go-tos, and it just, you would spend all your time writing code that then broke, and you'd have to. You pick the entity to which you delegate a task appropriately to what the task is that you want to get done. So if you ask someone 7-year-old to, help you clean up your, well, that's a bad example. I was going to say something about computers. 7-year-olds today maybe know everything about operating systems. I don't know, but you get my point. I don't have to give you an example. So anyway, on top of the underspecification of any task and the underspecification of the environment in which you want that task to be done. Oh, no one told me the copier was downstairs. Okay, well, you could have read the sign on the wall. There are changes. Whoa, who moved the copier to downstairs? And so you always have unforeseen variations. Always. This is the thing. So basically, for the real world, you can never assume that everything is completely static. This is one of the reasons why intelligence is needed for animals that can move around. And maybe one reason why some people want to say plants are intelligent for turning towards the sun. But I think I draw my threshold a bit higher than that, frankly. Okay, so yeah, so we also include in that, there's a line break there at the wrong place, but that's okay. We include, or like to include, adaptation there as well, because there are always changes, so you need to adapt. And the adaptation should improve the performance of the system so that a change, like, okay, the copier has been moved downstairs. Well, now I go downstairs to make copies. Now that should be part of this agent's repertoire of what it expects when it does that task again to copy. If it's in a different building, it should not assume that the copier has been moved downstairs, for example. It's capable of generalizing in a way that makes it more autonomous. So it doesn't have to be doesn't have to be told every time how to look for the copier or where it should be. I shouldn't have to say this, but I will. There are papers, of course, on autonomy. Some of them are really good, but whenever this term gets thrown around in robotics, in computer science, it very often is at the very low end of the autonomy scale, from a thermostat to a human, let's say. And so some of my collaborators really are annoyed by the fact. I think it's just a fact of life. I don't let it get on my nerves too much. It's just a different use of the term, but you should just be aware of it, that people mean very different things, and typically, because we don't really have, for example, existentially autonomous artificial systems yet. They're not really, even if someone says, I see sometimes papers with abstract, it says, we have built an AGI system that it is autonomous, and first of all, it's not an AGI system because we don't know how to build AGI systems. It's an AGI aspiring system. And I just, actually this morning, I found in one of my co-authored papers this mistake. I said it myself in this place, so please excuse me. What I meant to say was AGI-aspiring architecture, not AGI architecture. Okay, that's what we mean. And first of all, we don't know how to make AGI systems, and secondly, they're not really autonomous in any sense of the sort of everyday use of that word. Now, that doesn't exclude, people can say whatever they want in the introduction. By autonomy, we mean X, Y, Z. And then feel free to use autonomy as a term, because you've already explained what you mean by it. Even if it's just roughly explained, it's much, much, much better than what you see a lot of the time. In a paper in 2009, Eric and I wrote a fairly short paper where we proposed that we could operationalize autonomy by tying it to the concept of self-programming. And that comes back to the idea that, if a task is underspecified, you should be able to reprogram yourself in some way. The boundary between, then people might ask, well, isn't that just planning? It's like, should we call it programming if I say, okay, I'm going to turn left instead of right like I did last time because, that's just planning, isn't it? Yeah, well, you're acting according to some plan. And so we could use the terms differently, but I think there's a continuum from especially for systems that actually evolve their own ability to do planning, then it's going to be hard for us to separate it's an artificial separation, this separation between a planner and a plan. And you'll see how that is the case, at least in our system, in our approach. Because, remember, one of our requirements is that the system can grow cognitively. To grow cognitively, the system has to be able to modify how it self-operates. How it does that, of course, that's the research we need to do. And to what extent it needs to do that to achieve AGI, we don't know yet. But we have this hypothesis that in order to really achieve AGI, or at least to get there, we have to look at this phenomenon of self-programming. And how deep we need to go, we don't know. But the architecture, if you think of a traditional software architecture like I drew here yesterday with just boxes, you can always divide that further down into finer detail. At the finest level of detail, there's the line of code. And of course, we really don't have systems today that write their own lines of code. Or if they do, it's a very tiny fraction of the system's operation. And it's very well bounded by the designers so that it doesn't go haywire. As you increase the requirements of the system being able to bootstrap itself in some environment to learn a non-defined at design time environment, then there's fewer and fewer things you can actually decide beforehand about how the architecture should be. And so it might well be that a system that is sent to Mars doesn't have to, well, that's actually a certainty. An AGI that gets sent to Mars doesn't have to expect tennis balls coming flying at its cameras. And so its attention could essentially evolve or be evolved on Earth before it gets sent up in a different way and more efficient way than otherwise. And so how is it that the system can actually significantly tune its, let's say that this is the attention function here. I keep using that example of attention. And let's say that, well, it's a black box to you. It's a bunch of causal change that, depending on the input, will just do the right thing. Okay? And let's say that 30 or 40% of this thing, or more even, could be changed and or deleted for Mars as compared to a robot that was going to be placed, say, in the Amazon or in office space or whatever, then you're going to start to be hard-pressed to say, whether this is just tuning or whether it's actually redesigning the system itself. Now, if it's redesigning itself, and there's of course structure around this function that manages this change and manages its freezing once it's starting to work well. Okay, we're still assuming that the system is exploring various things, and the exploration can also be a parameter. Then you're going to have to come to the conclusion that, well, this function here is going to have to be implemented in such a way that it can be understood in some way by the system itself. So in a system like this, where's the plan and where's the planner? It's going to be really hard to separate them. That's our theory, in fact. But basically, you're going to need a uniform representation. You can't just have one language, say, for a plan, and then another programming language or another way of implementing the architecture. Because both the plan and the architecture may have to change significantly, which means this has to be machine readable and this has to be machine readable. Well, if you have two separate ones, and maybe then you have a sensing language, etc., if you have this many languages, you're going to have so many interpreters, different ways of doing it, and we really don't think that's feasible. If you could uniform these into the same way for representing the whole thing, then the whole thing can implement all of these things that we need. Now, of course, it remains to be seen if AERA can do that, but we're well on the way towards such a goal. So in this paper, we were talking about behavioral autonomous systems, where we're really talking about structural autonomy, the structure of the system. And when we talk about this, we're talking about adaptation, a very strong adaptation. That is, the whole system can improve its utility function as a result of experience in the world. And then more recently, I forgot to change the title there. Helgi and I, my recently graduated PhD student, wrote an article on autonomy and AI architectures, where we looked at various the state of autonomy with regards to cognitive and AI architectures. And in this case, we were talking about existentially autonomous systems. So this paper is online. You can take a look at it if you want. We could slice autonomy into 3 levels if you want. This may be useful for certain things. But this is just one dimension. Weak autonomy is systems that require some degree of human control to perform target tasks. Medium autonomy, systems that perform fully specified target tasks without human intervention. Of course, you see there's also another dimension that's missing here, because according to this, thermostats would be medium autonomy. And then strong autonomy is the system generates goals. This is really the one that matters to us. Yeah?
Are you also implying that the robot is its own sort of legal entity, it can do what it wants to, it doesn't need a human controller or anything like that?
Am I
Are you saying that there's someone in charge, the robot is owned by someone and that person says...
I see. No, I'm not talking about legal autonomy. Yeah, okay, I see what you're saying. With the existential...
They can do what it wants.
Right. No, then we're talking about the role of the AGI in society.
Well,
and
why we're doing it, yeah.
And we don't go there. No. We essentially, we say, okay, in theory, is this, if we take the robot as a case in point, because it's so easy to imagine, if we take a robot that we leave it wherever it is, assuming its body can withstand the, say, sand storms on Mars or the Sahara, or withstand the humidity in the Amazon, let's say, can it take care of itself mentally? I.e., if it needs lubrication, it knows where to go or how to make it from wood, sap or whatever. The autonomy there is about the entity's own existence, not its place in society. Okay.
I'm kind of more asking,
Okay,
whether
sorry.
that human control means, if it's saying without human control, does it also mean the robot makes its own purposes, or does it
Exactly, yeah,
does someone
exactly.
says, go wash my dishes?
Oh, yeah, this doesn't mean that it cannot take human control as input.
Okay.
This just means that it can do it without it if it has to. Okay? That it isn't reliant on someone guiding it. And you could, it's the intuitive use of the term. I mean, it's not common to use this term in English like this, but I will make an example. If you get a new helper, to maintain your lab or tune your stack of computers, and you never have to talk to them. It just every day the machines are running better and the place is cleaner, and that assistant is very autonomous. Okay. It knows its goal and it achieves it without you constantly having to say, "Did you check that corner there?" So that's the kind of thing, being reliant on versus being capable of taking in is not the same. Okay. Some examples. That's a toaster. That's a toaster. That's just a tiny bit more advanced toaster. That's pretty much a toaster too. That's not a toaster. None of these guys. On the scale of autonomy, something like this. On the scale of the kind of autonomy that we're interested in anyway. And you notice I have no scale on that. It's just, but the problem with a lot of these systems, like this, and this, does anyone not know what these three things are? Okay, good. So the self-driving Google cars, which got a driver's license permit in the US last year, actually. But you have to have a human sitting in the car for it to be allowed to drive autonomously. Are just like the toaster, designed for a very specific task. Now, it turns out that some parts of this task are way more complex than either of these, and even of that one, especially the sensing part. And that's why, to me, this is an interesting thing, because, at least it shows how amazingly impressive things you can do with statistics. And no one looking at a self-driving car would quote the often used phrase, lies, lies, and statistics, because it's obvious that this car is driving, and this is not a lie. It's driving, and it's not making any errors, and it's following all the traffic rules. To do that, and to do that without killing dogs or people or doing damage, it must sense to an extent that pretty much no other artificial system has sensed the real world before. But the problem is when you open the hood, that's a great use of the phrase, when you open the hood on this thing, turns out it's just statistics. Now, there's a workshop at AGI on statistics, and maybe Pei can tell you a little bit about that on Monday or next week sometime. But there is a movement, and it's a very strong one, probably because of the results of the impressive results that these people are getting, that you can solve intelligence with statistics. And I have a very good example of why statistics don't work for ultimately to explain or to implement intelligence to the level that we're interested in. I haven't tested this argument too much on these people because I haven't been too much in circles of these people for a while. But how many of you remember the Microsoft paperclip? Okay. How many were annoyed by it? Why was it so annoying? Well, it seemed pretty obvious to me that it was annoying because it almost never did the right thing. Now, that's a good reason, but why didn't it do it? Because if you actually, again, open the hood on that one, it was all also based on statistics. Now, these are advanced statistics. I mean, don't get me wrong. You can do a lot of stuff with this kind of math. But the assumption was that if you knew what the majority of people were intending to do when they did XYZ on the screen with the mouse, then if you followed the rules and you had the paperclip suggest what the majority of people, let's say 90% of people did when they did that, you would 9 out of 10 times be correct. So that's not so bad, because if you're writing something and the paperclip says, hey, it looks like you're writing a letter. Do you want me to put a letterhead on it and put your signature on the bottom and blah, blah, blah. It's no, go away. Okay, well if that happens once every 10 times, that doesn't seem so bad. In critical systems like this, if you put the Microsoft paperclip technology into a car like that, when you drive by the biggest intersection in town, your turn signal goes on, and the car starts turning the way that most people turn. And so you're using, in this system, statistics without knowing any goals. You're trying to infer the goals instead of doing it the other way around, maybe, and asking people up front, what would you like to do? And then you tell the system up front. So the annoying thing is that, because I don't seem to be average, it would be right. Actually, I don't think I ever had the paperclip guess right. So I had to Google around for a while to figure out how to kill it. And finally it died after some people had warned me that you can't really remove it. This is like, I have another funny anecdote on automation. At RU, they bought this really fancy weather monitoring system. It's in a glass dome on the top of the building that's heated so that it doesn't get icy. And all of the information from there goes into a computer that controls the whole building. So the air conditioning, the blinds, the lights, everything. And they forgot to put a manual override. So the first month was like hell, because you pressed the button and then the blinds went and the lights dimmed, and it just was totally, it was always wrong somehow. And it couldn't figure out how to override it. And finally they overrode it, and now it's okay. But it's like that kind of a, there is a blind alley whenever you do statistics. The statistics hide what's underneath. So you have, here is the stats. Here you got these somehow through some data mining or something. There's some info and so above here you may be inferring goals and doing all sorts of actions and stuff. But the system cannot get below this threshold. It cannot figure out, like we were talking yesterday about attention, it cannot figure out unless the engineers explicitly decided that we're going to make an exception here and we'll do it a little bit differently for the remote control of that slide projector, because you need to have higher temporal resolution than our data actually allows us to do. So we do this little thing here. We carve out that's for remote controls of slide projectors where you have to have a temporal resolution of decision making at 60 milliseconds or something. But for the rest of the system, you have some you've got some data mining. The system cannot go below this barrier because there is no information there. There's no mechanism that allows it to penetrate the stats. Pei can explain this much better than I can because he's been thinking about it for at least 2 decades or 3 maybe. But this is a really, don't take my word for it, because this is just scratching the surface on this problem. There's, and you'll probably flip-flop a lot as you start to read about it, because the stats guys are just have enormous results and very cool math. But you won't ever get away from this problem. What you need is a uniform representation that allows the system to analyze itself, its own operation, and causal effects in the world. This is really key. Thought I'd gotten it, but cause and effect. This is really what intelligence tries to figure out. To understand the world, you need to be able to, a system that wants to understand the world needs to be able to isolate parts of the world and do experimentation on it in such a way that we can infer cause and effect at a variable degree of resolution. So, and that's what I'm talking about here. The resolution of your world, the power of the human mind comes partly because we are free to pick the resolution at which we're scrutinizing cause and effect. So I can spend 10 years trying to figure out how to hold the bow on an arrow to make the beautiful sound that I know can be made from it. And while I'm doing this, I'm not really investigating exactly the powers in my muscles and strength and pulling, etc. What I'm really doing is listening to the sound at some level of detail, which is higher than this motor control. Consciously, that is. But of course, subconsciously, my mind is doing a lot of work for me because after a while, I start hearing more nicer sound, even though I'm not sure, I can't explain exactly what happened. And this is a very powerful, interesting thing, and I think once we have a handle on how this principle works, we can do a lot of interesting stuff with artificial versions of it, like I hope to do with AERA in the next couple of years. Okay. At this pace, it'll take forever to do these slides. Okay, so let me see if I can speed it up a bit. In my paper with Helgi Helgason, we isolated these 4 key areas, sub-areas of autonomy, as critical for defining autonomy or achieving autonomy. There are some others, I'm sure, but these seem to jump out at us as being really some key ones. Okay? And so we looked at several cognitive architectures in light of these. So the system's ability to learn, the system's ability to learn about learning, get better at learning, its ability to deal with the clock on the wall or real time, and its ability to manage its own resources. Pretty much none of the existing architectures that we looked at do all of these. Typically, they isolate something, and almost none of them actually talk about this, except NARS. Few of them talk about this, and few of them talk about that even.
When you say resources, is it internal resources like memory and
Yeah.
CPU time?
Yeah.
not like externally available.
No. Because that's then task, and you could put that in under learning. Because of the requirement of operating with insufficient resources at all times, and you could, I guess, say, okay, time is a resource and merge these. It's easier to talk about it if you separate it out, we find. But when we say real time, we're not talking about hard real time, like a video player has to play every frame for 1/30th of a second before it shows the next one. Otherwise, you'll feel like time is slowing up or speeding down, speeding up or slowing down. And that's not what we mean. When engineers see this, they oftentimes think hard real time. No, we're really talking soft real time, as we call it. Soft real time is really the ability to manage the passage of external time external to yourself. Now, to manage time that is external to yourself, you have to understand something about the speed of your own operation. And then that's how these are tied, actually. Because, as I mentioned yesterday, anyway, yeah, let's move on. You could draw it sort of like this and split them a bit further. Learning, these parameters matter. Rate, capacity, integration of what you're learning now with respect to what you have already learned. The very many methods that you could use for learning, and the styles. So, meta-learning, you have introspection, self-evaluation, various ways of meta-learning types, and then reconfiguration of your own architecture. And resource management, you have to be able to prioritize. Ideally, you should be able to have multiple simultaneous goals, which might or might not be contradicting. And the question here is also of what kind of resources do you control? Because most of the cognitive architectures that claim to have attention, this is really the attention branch, they only manage some sorts of resources and not others. And then you have the real time, this granularity of your temporal resolution, whether it can be varied. The uptime, do you have to go offline at fixed intervals to garbage collect? The reactiveness, how long does it take you to realize that an interruption is important? And the planning horizon, how far into the future are you thinking? And here's the comparison chart. I'm not going to spend too much time on it because it's much better to just read the paper, and really I don't want to repeat the whole paper here. But this was our result.
Didn't get OpenCog in?
Sorry?
OpenCog's not on the list?
OpenCog is not there, no. Partly this list was chosen because of the available documentation and or the available code. The clarity of it and our ability to assess the prior dimensions for each of these. And for example, my own old architecture, EMIR, is there not because it's such a brilliant piece of work, really, because it isn't, but it was an interesting system, at least in some circles. But from the AI perspective, it's very, very close to what Rodney Brooks was doing at the AI lab at MIT in the 80s. And so instead of using that, we use this one. It's a bit more advanced because it has the ability to have knowledge bases, and sort of it's kind of a hybrid system. The reason for this one being here is because my close collaborator Eric Nivell is the author of that. It's not because so much has been written about it, but because we could simply ask him. And unfortunately, actually, it's a bit sad that how little there is available on that architecture, because this is really the reason why we're working together, frankly, he and I, and it's a precursor to this one. The reason why this isn't in there is because I didn't want to fall prey to some criticism that we already got, which is unwarranted, that of course our system got the highest score. This is not our system. This is a precursor to our system, and it's the reason why we did this system. So just so you know, we didn't write this paper to advertise our own work. We really wrote it because when Eric and I started working together, he convinced me that a lot of ideas in here could bring us further on the autonomy scale. And of course, it's a multidimensional comparison. So we did a rough sketch like this to sort of highlight some of the differences between these various approaches in these architectures. By the way, these architectures are very different. They have very different main goals. For example, EMIR, my own stuff, did not have the goal of achieving AGI at all. In fact, I deliberately decided not to include learning in it because it was done in the early 90s, and I just found that machine learning at that time was pathetic, and I didn't feel that it was worth my time. What I wanted to do with this architecture was integration, which is essentially what OpenCog seems to be doing now, although it's more advanced than this. So you've got these three kind of axes, if you will, and the arrows highlight some of the differences, some of the contrasts between each of these. So this thing is fairly static. It does one thing well, which is, or two things I should say, two things well. One is the integration of modes, sensory and actuator control, and it also does real time, way better than this one. There's no meta inspection. There's no generation of new components, although I imagine that you could do that at some point in the future, because it is kind of, it has that same flavor that the subsumption architectures have, that it's not so hard to comprehend from a computer science perspective. You come into this, you don't need a lot of AI training to understand it. SOAR, which is of course a staple in the history of AI. And they're trying to sell it a lot in the AGI circles, and frankly, I'm not buying it. But some people seem to. So one of the reasons is, so these are just stand-ins for three very different approaches. You could think of them that way. And this is sort of like good old-fashioned AI. This is the not really reasoning, perhaps, but yeah, I guess reasoning-based or logic-based in some sense. And this is just a completely new dimension. And this is essentially where our constructivist approach comes from. Okay. Before we go into the next thing, any questions on this? You can interrupt at any point. Yes.
Should we?
Okay. You were first.
When was this done, this slide?
2012.
So it's recent.
Yep.
My question is quite general, so maybe should I ask about autonomy now or in discussions?
Feel free to ask.
Okay.
And then feel free to ask again if you move on too quickly.
You said that you was talking about autonomy, and I was looking at it and coming to to the opinion that you can't define autonomy. And
Okay.
it isn't you can define autonomy, it is just undefinable.
It's undefinable.
Even in operational sense, you're talking about because autonomy is not isn't a property by itself, but it is a thing tightly connected with interaction.
Yeah.
It is a property of interaction by itself.
Yeah. It is.
That's why it turns out we are talking about thing that isn't there.
Yeah.
Maybe we should. Maybe it is much more understandable if we are looking from interaction. It would be describable.
Excellent point. And that's essentially why we had to do this breakdown. We had to pick sort of what do we think of as the underpinnings of autonomy in the way that we interpret this concept. But it's and then you break that down. But it's like any other human natural language concept. I mean, it's hard to really become specific about it, but it's fine to use every day, and then you have to, and then you're building AIs or AGIs, and it just suddenly doesn't make too much sense anymore. You have to go back to the drawing board to figure out what do your terms mean. So yeah, I agree. I think, and even these, you see, introspection. We didn't have proper space in the article to explain exactly what we mean by this, but I think there's a couple of lines there. But that's, of course, not really sufficient if you want to be. However, the point actually for all of this is that if you don't even mention it, like the exclusion of time in so much of the AI literature, there's something very strange about it. And just by raising this issue of autonomy being an issue and having an impact, we're saying this kind of autonomy that where you have some of these, at least, that maybe say 80% of people would agree that that your system has some sort of introspection capabilities. Then we can say, well, okay, what kinds of introspection capabilities does it have? At least it has some. The problem is, like, you've got the current systems. Let me think. Let's see. So here are levels of abstraction from, well, let's see, memory, messages. Let's say you have, here are, some good examples here. Levels of abstraction. So you can look at these architectures at various levels of detail, and of course at the lowest level they're all bits because that's how they're implemented on digital computers. But that level really isn't that interesting to us. So what's interesting as for cognitive architectures is always above the bits and the words. So if we had something like this, here is the existence level, like autonomy relating to your own being and your body and your energy coming in. Plans, you've got bits of things, tasks. Then you've got a lower level there, concepts, moves, etc. Then you have the system memory of messages, pieces of info, etc. The problem with a lot of these architectures is that they use terms from here, and then when you dissect it down there, you see sort of what's behind their use of the term autonomy or learning. You remember my slide about so many types of learning, right? Well, they use this word learning, but when you start to dissect it, it's really just a tiny little, update message to a reinforcement learner in some tiny part of the architecture. So it's not like, the architecture sounds like it's autonomous and it's learning, and yes, I'll call it an AGI architecture, but really it's an AGI aspiring architecture that really isn't autonomous except on some 1 or 2 variables, and it's not really learning except for it's tuning some tiny parameter in some tiny part of this architecture. And on top of that, you've got all of the things that we have listed as being important, maybe not all of them necessary, but certainly some subset of them necessary for us to even use this label. And you realize that they're not talking, they don't deal with time, they don't have any sort of decent attention, etc., etc. And so, yes, you've got that one and you've got that one, and when you dissect it, it turns out it's tiny. So what we're really saying here is that by raising this issue of autonomy, we're just, emphasizing yet another word in here, autonomy, that is being ignored at the high level, even in a tiny way, even as a variable. You've got papers all the time in AGI about architectures that have no concept of time, and people even say time isn't important. Time is infinite.
You were talking about the scale of autonomy and coming from a stone, as I remember, to human. And but even humans, they when acting autonomy, they are doing something for others, because in general it is so. Then maybe I just got an insight while while the slides was going, and maybe it is some taking or even appreciating limitations on interaction. When you do comply with the common limitations, then you can be seen as autonomous. And when you break these limitations, your autonomy ends with the speed of light. Because if you don't, how did you said about this robot that should be acting in Amazon? It should limit itself to some physical environment. That it shouldn't be falling to the river when it takes water.
Right.
And that lets him to be by itself.
Yeah, I think we can come back to that. I think we should move on. I wanted to tell you about attention a little bit, and then in the last part we'll get into just in a very quick and dirty way into situatedness, but at least you'll get an insight into the flavor of how we think about that. So why do we talk about attention? Why it's yet another one of these words that is being left out of what we feel is a critical term or concept to AGI work. The source of attention, the need for attention, comes from this fact, that unless we assume that there's a God-like intelligence somewhere, or we're just about to build one that knows everything and foresees everything and can do everything, then if you don't have that, anything short of that falls into this category of not being able to deal with everything at all times, having limited capabilities in its resources. So even the smartest being that we know of or even can imagine must come equipped with some mechanism for dealing with its shortage of processing, inferencing, learning, and knowing capabilities. And this is why higher intelligences have something that we call attention, typically. I already mentioned this. Many existing AGI-aspiring architectures are based on this assumption of infinite computational resources. I've said it before, I'll say it again. Basically, if you assume infinite computational resources, you are not doing AI, because you don't need intelligence if you have infinite computational resources. Intelligence is essentially existing because we don't know everything, and we have a real-world clock, and we can't spend all our lives thinking about this one tiny thing about whether a step will break in the ladder when I go up to the attic. So that is why intelligence exists. It's because time and resources, external resources, are limited. Energy is limited in the world. But let's say that we only want to build a system that does fairly simple things. Yes, we want some sort of an AGI, but we can assume that our resources are going to be available sufficient resources are going to be available all the time. Still, even there, you could make use of attention, because attention will help the system focus on things that matter and ignore things that don't matter. So why process all of the visual input all the time when you could do away with that and just process what matters? Why do we have peripheral vision? Why does the peripheral vision we have not include color perception? Well, it's because in our periphery, what really matters is the size and speed of objects. In case a rock is falling on your tree, or a lion is launching towards you, this is really why that is like that. And it's exactly the same point. Basically, our retina is organized such that we're highly sensitive to motion on the edges. Well, actually, most of it's highly sensitive to motion, cannot detect color. You can do this experiment if you haven't already. Take something with the color, look at a point on your desk, and then move it. And you'll notice, if you pay attention to it, there's that word, you'll notice that the color disappears. Or if it doesn't work for you, have someone bring a colored object whose color you don't know into your periphery while staring at your finger, and try to tell its color here. You can't, because you don't have the sensors for it. So that's exactly what nature does, and that's exactly what we will do in AGIs. But only very few existing architectures actually make any attempt at addressing this phenomenon. And if we keep ignoring attention as a mechanism of cognition, then we just are delaying the AGIs from coming. So our stance is that for AGIs, attention is really critical. It's an absolute necessity. Have you heard of the cocktail party effect? Who's heard of the cocktail party effect? Oh wow, only 4 or 3 or 5, 6. Okay. Okay, a bit more than I thought at first. Good. Well, here's the question. You're standing. You're at a cocktail party. People are standing up. This is probably America. People talk very loudly. They all have food and glasses in their hands, and they're talking. And for some reason, there's some people standing around right next to you, behind you, even maybe closer than the person you're talking to. But you don't hear what they're saying because you're listening to this person in front of you. And when you're done talking to this person, you can pretty much recall everything that you said. You can even maybe repeat it close to verbatim. If you're asked what the people behind you were saying, they were talking just as loudly, you heard it just as loudly in your ears, you can't say any of it. Now, suddenly someone from across the room calls your name, not so loudly. It's fairly faint, but immediately you look up. How is it that we can do that? What is going on here? Well, this is typically what people call attention, and this is what got the modern research on attention started in psychology. If you explain it from the informational stance, what you have to conclude is that somehow there are filters operating in your brain that essentially exclude the words that people are saying right behind you from becoming words in your head, heard words. Of course, if you are aware of the people behind you, you may notice that they're kind of loud, and you may walk a little bit away from them. But you may still not really be paying attention to the content of what they're saying. And the engineering way of explaining that is that you've got this signal coming in, and you're probably all familiar with the concept of a filter. Only part of the signal gets through the filter. So that could explain how you're able to filter out what everyone else is saying around you. And you may not even notice, I don't know if you've ever experienced this. Sometimes you're sitting maybe in your hotel room, and then suddenly the air conditioning shuts down, and you go, oh, I didn't notice it was on. That's the work of a filter like this. Basically, constant noise gets filtered out. I used to live in New York, Manhattan, and I never really noticed the droning of the traffic until I went back home to Iceland to visit my family. It's like, wow, it's so quiet here. So, but when I got back there, it didn't really bother me. The filter just turned on. But it just doesn't explain how you can hear someone calling your name from the other side of the room. So what's going on there? Well, if this is filtered, then, my name is going to get filtered. Aha! It's an intelligent filter. Okay, of some sort.
Is that an I in a computer thing?
It's not a term or anything. Let's put it this way. This filter has some AI in it. So in psychology, you had these theories in the very beginning that were all based on the filter idea, and then the cocktail party effect came along and kind of started people on discussing, when do you filter? So is it like this maybe? Is the filter designed this way? So all of the things really get through the sound stage. Let's say this is the sound, this is the words, this is the meaning, higher level meaning, and then etc. And some of it gets through some way, but only the main signal gets through all the way, and this is really, and then the thing that gets through all the way kind of results in everything else getting deleted. So you can't, from your memory, so you can't even recall that you, in fact, did hear what they were talking about behind you, but your consciousness is simply not accessing it. And so people said, okay, well, this filtering must happen later. I haven't seen anywhere this idea, but I'm sure someone came up with it. You could maybe say that because you've learned your name so well, and it does really kind of only work for your name, to be honest, it's already programmed the filter to let it through. So something approximating the waveform can actually get through the filter. I don't know. In any case, you can imagine way, more ways of designing something like this. I'll show you an example of a hybrid filter. The main distinction that people made was, okay, is the filtering done on the signal or on the meaning? These were the two main categories that people argued about. This is just history. I think they're still doing it. Here are some examples. So you see this around 60s, early 70s. But in fact, what people came to realize is that there must be at least two types of attention, and maybe they're working in parallel, and I'll show you an example of that in a second. Top-down attention is task-driven. So if you're doing something, some task that involves certain entities, like playing tennis, I keep coming back to that example, you will be highly sensitive to yellow balls. So if you get 2 or more yellow balls on your court, you'll notice immediately. I don't know if you've ever seen this video. There's a video of some people playing basketball. See, I think one of the baskets over here, and they're playing basketball, running around. In the background walks a guy in a bear suit. And you're given the task at the beginning. I ruined it for you now. Sorry about that. You're given the task of watching this carefully. What people do is that they think, oh, it's a basketball game. Okay, and they pay attention to everything but the guy in the bear suit. And then after the video comes to the question, did you see the guy in the bear suit? And people go, oh, whoa, and they go back, and oh, it's there. It's a very strange effect. I mean, it really works if you don't know it, that is. And so there is some top-down attention mechanism that's essentially tuning all of the pipeline, if you will, of processing from the signal and upwards so that certain things are more salient than others. And there's obviously also bottom-up attention, because otherwise, if you hear that loud noise, you're going to jump no matter what task you're doing. So there's stuff that gets through no matter what. There's sort of interruptions. So AGIs really have to have both, in my opinion. Now, tuning the ratio, managing the balance between top-down and bottom-up, because remember, this is the management of how you use your resources, is the task of the attention system. This is an attention system from Knudsen, a psychologist, and this is a fairly recent one. It's from 2007, and it combines both top-down and bottom-up. He's working with neural representations. Frankly, I don't know too much about this. I can't really tell you a whole lot about it. But when we were doing our background research on sort of what's the state of the art in psychology in attention modeling, and it has a long history. and psychologists have done a lot of work on this. Of course, they haven't been doing it in the AI frame of mind, so it's hard to take all of these ideas. You can take some of these ideas, but you can't really take a design like this and implement it. You have to do a lot of translation, and that's what we did. So now let's take a break for, say, 15 minutes, and we'll get back here 3:40 left. Okay, so let's continue. This is a design for an attention mechanism for AGI aspiring architectures. This is essentially the result of Helgi Helgason's PhD work in my lab over the past 4 years. We think this could be useful for many AI systems, but we're really doing it because of what I've said before, which is that we think that AGIs will, out of necessity, have to have pretty decent attention mechanisms. And so this is just an overview picture. I don't expect you to understand all of it at once. We'll dissect it and talk about it piece by piece. There's Helgi's thesis probably somewhere online already, is my guess. But if you're interested, you can send me an email and I'll mail it to you. Let's talk about this part first. It's pretty obvious. You've got there on the right-hand side the sensory devices and actuation devices. This is not necessarily a robot, but it's very easy. Again, that's my favorite way of thinking about an embodied or operating AGI. Actuation devices would then be the robot's body, and sensor devices would be cameras and microphones and stuff. The environment, of course, is the real world, or some environment of equivalent complexity or higher complexity. It could also be a simplified environment that's still real world, that is still has a real-time clock, an external clock, etc. But that's not necessary for the moment. What we have, I guess the main, one of the key outcomes of this work is that we saw it necessary to separate processes and data in a very clean way. However, processes can, in AERA at least, can be data. So if you have an evolving system that's programming itself, some of these processes, you could think of them as algorithms, could be up here, and they could even be running, instantiated and running at the same time as their input as data to some other processes. And that's a necessity because in a system that's evaluating its own progress in learning and or its own performance at runtime, it needs to be able to say, well, I've got two processes, let me actually kill one of them or just let one of them run. Let me decide how that's going to be. Well, you take the processes, you make them data, you put them into another process that actually decides which one in the current context should live, etc. So just to give you a bit more hands-on understanding of how we think about this self-programming, self-organization mechanism. Data have saliency, so all data is marked as to its current importance, and the current importance, the clock for the system in AERA, in the way we implemented it, is very high. We are updating, assuming decent parallelization, which we have been able to achieve on not so many cores. We have thousands of data items processed per millisecond, at least. So anyway, this is kind of, we're just getting started now. This, you can already tell, this is not the attention mechanism itself. This is just some assumptions about how the architecture is actually organized. Okay. So this is an attention mechanism that was designed recently and has partly, oh yeah, I didn't mention that, it's only partly implemented. What I'm going to show you here is only partly implemented in AERA at the moment. But all the main principles of it have been verified to be solid. So you got the goal-directed data prioritization function up there, the dotted line box. So these data items are essentially marked for priority based on the system's current goals. This is the top-down part. And the data is biased based on a massive and continuously ongoing pattern matching effort. The goals and predictions could come from a human or something else. That's why we think this could be fairly easily used for more standard run-of-the-mill AI systems. Don't restrict ourselves necessarily to AGI. But in AERA, the goals and the predictions are all generated automatically by the system. And a key part there is the attentional patterns, which I'll come to later, which are being used to do this matching. And then we have bottom-up evaluation of data and biased as well. I'm totally blanking now on what NDDP stands for, but it's something obvious that'll come to me in a second. Yes?
Novelty-driven data.
Novelty, yes, novelty, yeah. That's what it is. It's essentially, it's the bottom-up part. And then you have something for processes, which works a similar way. This is process, what does it stand for?
Experience, something.
Yeah, experience, yes. Experience-based process prioritization, or experience-driven process prioritization. And so the processes, and this is contextualized. So the context is actually used to say, okay, this process, in my experience, this process, that process, etc., all of them, all the time, this is always ongoing. In this context that I'm currently in, that process has worked so-and-so. So I'm going to prioritize it that way. I'm going to give it a score. And there's a generalization mechanism here which is not really been implemented yet, but whereby the better this works, the better this thing works, but it still works without it. It's just going to be slower at learning, and it's not going to be as good. But the generalization, you could sort of see, okay, you've got processes, and you're saying, and the system is saying basically, well, actually, I don't have any experience running that process in this context, but it's very similar to that other process, and I have very bad experience. So that's a better guess than just saying 0.5 or whatever, or giving it some heuristically generated number, predicted value or utility for that particular context. So And in fact, this is all you need. And we bias the processes. Now, this is computationally extremely expensive. But it just so happens that if you have if all of your architecture is already organized around the necessity to score the value of some process or some data. For example, that's what you really need to do, for example, to plan anyway. Because if my goal is to pick up this thing and I've already seen that if I do it this way, I'll knock it, I need to, for any goal, prioritize the ways of doing things and what values to put on the parameters, weights, on the muscles, etc. I already need to do that, so that's all available anyway. That mechanism is there, and that changes the cost of this attentional mechanism significantly to making it almost obviously just part of the control mechanism of the architecture. So in this sense, you're actually ending up with an attention mechanism that doesn't look too different from a control mechanism for an architecture. And I think this tells us something about, if you buy the argument that we need attention and you look at this system and you see, in fact, how extremely effective it is at answering all of the problems that the psychologists have been dealing with for over 50 years and modeling sort of how the cognitive system of humans does this, you start to think, well, actually, maybe this is telling us something about how we should organize our architectures. And for example, we assume completely data-driven architectures. This is the least overhead. This is the least expensive way of processing, if you can do it efficiently, especially if you could have it in hardware. If you could have a completely data-driven CPU, that would be extremely efficient for this. So a key part of this is the attentional patterns. Yeah, so basically, let me just say that essentially the basic principles of this, separating the data items and processes out, giving them a score, updating them all the time with regards to the current context. This has all been verified in AERA, how this works, and that it works. And it even works for very complex tasks, which you'll see when I show you some videos on Monday. Maybe one of the very new things here is the attentional patterns, this idea. I haven't seen it anywhere else. And to give you an example of what that could be, so if you're looking, if your goal is to find circles, you can put into your data stream filters of this type that bias the data coming in already at a very low level of processing based on a simple pattern.
What difference from filter?
Because it doesn't block things, it just gives them a score.
I see.
So it's a range, it creates a gray area. And then of course you could imagine putting contrast control on that.
You still get in common the other objects.
Yeah, the effect is that if you have a lot of resources, computational resources, you can be doing more with the input. But if you're running short, you will cut the least expensive things out, up to the very most important thing. If your scoring mechanism works properly. Now, of course, it's going to make mistakes, especially when the system is learning. And we're assuming that AGIs are learning all the time. So you end up with essentially a system. You end up with the conclusion that AGIs will make mistakes, like philosophers have said for hundreds of years. Well, not maybe about AIs, but hypothetical scenarios. Not sure how useful this will be, but yeah, sorry.
Do processes and data items get resources probabilistically, or just the ones with the highest priority?
There's no probability. Probability is all emergent from the causal effects of the deterministic architecture that we have.
Because this morning we learned that in NARS, it seems like the things are assigned a priority score and then get resources in a more or less probabilistic way, which I think is done to ensure that even the lowest items get a chance. I mean, there may be different processes, obviously, but...
yeah, I'm not prepared to really comment on a comparison like that, because probably my guess is that we're comparing apples and oranges, actually. Because remember, I'm carving out some tiny part of this big thing, and since, well, there are some, in principle, similarities with AERA, between AERA and NARS, but Eric will be better, keep that thought and ask Eric, because he'll be better at answering that properly. Okay. Especially if you put it on the wiki, he may even answer before he comes here. And of course, if you do it on the wiki, I won't be so nervous in answering it as doing it live and having to eat my hat afterwards.
I just came up with it there, so...
Yeah, yeah. No, actually, that's the kind of question that you can hardly ask about any other architecture or comparison except AERA and NARS. So don't get me wrong, it's a good question. I'm just not prepared to answer it properly. So this is based on the principle that in any environment, the system is capable of identifying entities that it can isolate and represent explicitly in its knowledge representation scheme. And each and any entity can have 0 or more properties. Okay? And then the structures of valid patterns is subject to rewriting rules. Pattern is one or more conditions. Conditions can be a particular value or a range or the outside of a range. And you can use, like we had in the example here, you can have wildcards, any, for example.
Greater than, less than, maximum, minimum?
Sorry?
Greater than, maximum?
Yeah. And exactly. See, so the range can have...
oh, okay.
Yeah. It's actually surprisingly simple, and if I was seeing this talk that I'm giving now and hearing this for the first time, I would say, there's not much you can do with that. But if you want to call it attention, fine. And then I'd be very skeptical, and then I'd look at the video and I'd go, really? Is that possible with just this simple mechanism? Okay, interesting. So, unless you have some more questions on that, I'd like to slide back into the last subject. Yes?
Can an entity have 0 properties?
To the system. To the system. Yeah. It has exactly. Yeah.
In this, is it a particularity of AGI systems or your system or in general? Because
Ours.
Yours.
Yes.
Not AGI.
Well, let's take an example. If I tell my AGI, there's such a thing there's a thing called a car. It knows that there's a car, it knows that entity, but it doesn't know any of its properties. If it believes me, that is.
Okay.
So you see.
So
Okay.
it
it can represent entities that have no properties, yes. So I wanted to give you an example. I hope I'll do a decent job of this. I haven't gotten to this in about a year, and we'll see if I remember it. If I have to go back, we'll go back. But basically, and it's not a coincidence that I choose joint action coordination, because you'll see in the video, the evaluation of AERA, what we did, we used interaction between the system and the person in face-to-face interaction. So that's why we have this example. But first, because probably most of you haven't really thought about dialogue as a phenomenon or as a subject of scientific investigation, I wanted to show you the kind of thinking that we have in what exactly is going on when two people interact and communicate. And that's what this first part is on. So we'll first go through this example. Basically, here's person A1 and person A2, two humans interacting. And in their planning / behavioral repertoire, you can say that that each of them has a state, a mental state. We assume that both of them have a common goal, a shared goal, that is to do cooperative dialogue. And they have perception and action, and to communicate, the only way is for one's action to go through the other's perception and vice versa. So that's the way each of them has a perception-action loop. The only way to communicate is there's no cables between their brains. All you can do is move muscles and air and your arms, etc. And for the other to interpret. Now, this kind of modeling dialogue and communication, of course, has a long history in science. We have our view on it, which is, I won't say too much about that historically speaking. Basically, it's possible that some psychologists and especially linguists would disagree with this model. But to cut a long story short, our model of communication is essentially a negotiation model. That is, everything, what controls the progress of a dialogue is essentially implicit agreements to move on. And just to take an example of what that means, if I meet someone in the hallway and I make myself likely to speak to them, and I even say hi, it's up to the other person whether to accept that offer for interaction. So they can walk right past me as if I don't exist. But if they stop, we think of this as they agreed to make a contract with us to at least pay attention, to give us some time of their CPU, okay? And then for each interaction, for each utterance, typically one person says something, the other, well, if it's a face-to-face, the other will be looking around and listening, maybe nodding, and then they will speak. If it's a question-answer kind of scenario, like where's the bathroom, the interaction can be very short, either one or two, or two or three turns. So, you have, where's the bathroom? It's over there, thank you. Or where's the bathroom? It's over there. And nothing. In some cultures that would be rude, and other cultures that would be fine. In some scenarios it's rude, in some scenarios it's fine, it varies. But the idea is there that the person can stop and look like they are going to help you, and then you say, where's the bathroom? And they say, "Pah," and they walk off. And so that means they agreed to your contract to actually start a dialogue, but they didn't agree to the contract, or maybe they didn't realize that you were asking a question. There could be a lot of things that were happening, but they walked off and they broke the contract. So from your perspective, from their perspective, maybe they thought you were telling them to fuck off. I don't know. But in that case, the communication failed, in fact. Because the communication already started, so that means we both agree to exchange information. We are in agreement that we want to communicate. And so that's the biggest contract that gets written right when you stop and infer from their behavior that they want to talk to you. So anyway, I could go on for hours on this. I won't. But basically, in their mental architectures, they have states. I like to call this fluid states. Eric doesn't like me to call it fluid states because we need to have a common terminology when we talk about AERA, so we just call it state. To a computer scientist, this could be easily misinterpreted because the kinds of states we're talking about is not like finite state machine states. It's very, very far from it, but let's just stick with state for now. You've got, associated with each of these states is a set of activated, remember the processes, is a set of activated processes for perception and for action. And the nodding and the looking gets triggered, and the eyebrows maybe, if someone asks you, did you meet a stranger in the hallway, they stop, and maybe you think, oh, they're going to ask me where the bathroom is, but they ask you, where's your wife? And the eyebrows go up. Anyway, there's you can look at it this way. You've got a perception for a particular behavior or a set of behaviors that's part of the behavior repertoire of the other, and that's what you're expecting. So, so in this case, this guy is talking. You've got these states are aligned or coupled. Why are they coupled? Because both of the agents share a goal, the goal of communicating effectively. Okay, and so they both have perceptions on, and A1 outputs a behavior that's part of its behavioral repertoire, and agent 2, through its feedback loop, perceives it because it's already activated the proper perceptors, if you will, perception capabilities, and it's what was expected. Oh, they just asked me a question, and this question is something that is part of what I recognize and understand, and I do know how to respond to that. In fact, as a result of perceiving that utterance, the state of A2 changes, and A2 makes a decision, and let's say there was a question, makes a decision to reply. So there's some behavior generated from A2 that's then now perceived by A1. So A1 knows now that A2 is going to reply to their utterance based on the fact that they raised their eyebrows and opened their mouth. We're talking decisecond analysis here of human behavior. It may seem a bit strange to you, but there's a reason why face-to-face dialogue just feels very different from much more personal than telephone interaction, especially with people you don't know, because there's just so much more information being transferred all the time. And this is actually a very good example of how intelligence systems are always on. If A2 started to look in some other direction or do something that was unexpected by A1, then they might stop and say, what are you looking at? So the dialogue is essentially always being maintained by the two perception action loops. And A2's behavior that gets produced is recognized by A1. This could be as much as just looking back or looking up and scratching their heads, which is a clear indication that they're thinking about what you asked. Could be any of these things. And so due to this fact, A2 makes the decision that that A2 is in another state, and that automatically changes the state of A1, because now they expect that they will get a reply of some sort. Okay? And their states are coupled again. So you got these transitions that are based on information that's flowing all the time. And this is not, and this might indicate that the whole system, the whole architecture just jumps from one state to another. It's not like that, at least not in AERA. It's very different from, as I said, a finite state machine. Basically, you have a large number of processes, maybe even in the thousands, and some of them are above and some of them are below a threshold of activation. So by these 50 processes moving above and these 10 going below, we call that a different state. In this case, these kinds of transitions of these processes have been learned by these agents. And that's why it's more like a fluid state than a state, really, from in the computer science sense. So any question here? Is it clear? Good. Either it's totally unclear and nobody wants to ask, or it's Friday and you want to go have a beer, or something else. Or you understand, which is, of course, what the real truth. Okay, so here is an example of a model, essentially in AERA, and I can't really go into detail on that now, but we'll come back to this example. We'll look at it again in light of the video that I'm going to show you. But in AERA, all knowledge in the system is encapsulated in what we call models. And they can be hierarchical, there can be models of models, etc. I'll go into that in detail on Wednesday. But for now, we will have to skimp on that a bit, and you just have to bear with me. Models are fairly short. They kind of look like an equation, a short equation. So from somewhere, A1 is now an AGI, and A1 has a model of a behavior that is moved into its active, into its group of active models. And is part of alpha of A1, okay? So that's the state that A1 is in right now. It includes model MN. Now, the AGI outputs some behavior J, which is perceived by human, or actually, no, let's see, no. Well, it doesn't matter, actually. These are two AERA agents. Let's just think of it that way for now. So A2 has as well a model that allows it to perceive that behavior and understand it. And the same thing happens essentially that as a result of transitioning from beta to whatever letter that is, I think it's Y actually, or gamma. A behavior is produced, which is then again processed by a model that predicted it, and thus A1 understands it, and as a result of this, the model MN that we saw in the beginning there gets strengthened. its experience counter is increased and its success counter is increased. So all processes have experience counters and success counters. It's slightly different from the way Pei does it in NARS. But I really think we can unify it and come up with an even better idea than we have right now. So that's really all I have. What do you think?
I think that's a really difficult problem to start with.
Oh, a good point. A good point here from the teacher's pet. We knew that we needed a scenario that no AI system could solve at present without lots of hand waving. So we chose an interview scenario with a human and a human. Now we don't use video, and we need to get the frame rate so that we don't dilute the system with just pixels. We transfer the interaction of two humans doing an interview into a sort of a virtual version of Skype. So basically we track the two humans. So it's like Skype, except I see you as an avatar and you see me as an avatar. And this automatically, it's a real-time interaction. All the speech, all the movements are real-time. But you see these avatars, and these are geometric entities, and that's what AERA is watching, not pixels. So we have a simplified interview scenario that AERA is observing and learning from. Then AERA jumps in and does either the interview or becoming the interviewee and tries to make it happen exactly the same way. Now that's a non-trivial problem, and we knew we needed a non-trivial problem to really make people pay attention to this work. And actually, it turned out much, much better than I had ever hoped. So I'm happy to say.
If it works, that's very impressive.
Sorry?
That's very impressive.
So is the interaction verbal, visual, auditive, cognitive?
Yeah.
Okay, and when can we see it? I want to see it.
You want to see this now?
See how it works.
Yeah, you could jump the gun and go to the HumanOps website. The videos are all there. HumanOps. Or you can wait till Monday.
You're going to make us wait.
Yes, I did have one question online. Let me see if I can pull that up here. Where's my cursor? Let's see. And I just answered it. Where is Hazrat Ali? Hazrat Ali. He's not here. Oh, okay. All right. Well, I did have the question from the concept of the mandatory component of learning in an AGI. Does it mean that the AGI is purely about unsupervised learning? This is the key question. And I had some time to answer it in the break. Here's my answer. Basically, being capable of unsupervised learning, of course, makes you a more capable system. Being capable of both unsupervised and supervised is even better. And maybe if you're an extremely flexible AGI that can actually adapt to any environment, you may have to start from such an impoverished bootstrap code that you do need supervision, like human babies do, in fact. Whether they actually really need it or whether it's a historical coincidence, that's something I can't answer. But it's possible that if you have a very highly flexible AGI, you simply cannot avoid having requiring supervised learning in your early formative stages. It depends, on a lot of things, but this is other things being equal. So that's it for now. We'll have some, I hope, more questions on Monday from you guys, so we can, and especially now that I'm starting to introduce some of the AERA concepts, I think the humanhubs.org website. Feel free to look there as much as you want. You'll be just better prepared, and you'll have better questions. Yes.
How about time for the question that I asked yesterday?
Oh yeah. Okay.
I didn't post.
Excellent. Yeah. Can you repeat it?
Yes, because that you was talking about the seed that self-programming architecture must be growing, which is obvious, and it will be developing subject. So my question was, how do you avoiding that this growing, that this self-developing of the system won't be guessing and blind guessing?
Yeah. So it's really about the need. This question has to do with how much guidance does an AGI need in its formative stages. If you as the designer are very good at coming up with the key heuristics that enable it to bootstrap automatically without any supervision, then of course that's the preferred way, because then you don't have to worry about it. And it's possible that for many environments such heuristics exist. But if you are, let's say, developing an exploration robot for a distant planet, and you really can't have high-resolution images from that planet, that would seem pretty impossible unless you know exactly the chemical, all the chemicals on that planet's surface, and whether it has a surface, and whether it's solid or liquid, etc. The more information you have like that as a designer, the more likely you are to come up with heuristics to make it completely bootstrap itself. But for AERA to learn this, this interview, we had to do somewhat of supervised sort of teaching sessions. So that's a case in point. In fact, some things were easier for the system to learn than others. So we did extended scenarios for the things that were more complicated. We didn't really see beforehand. It's very hard, just like the waves on the cellular automata, it's very hard to see exactly how it will happen. And since this was the first time we built the system and tested it strongly, it was very hard to foresee. Of course, once you get to know a system better, the better you get at doing that. But to some extent, it has to do with how well your heuristics that help the system bootstrap itself map onto the variation in the environment that the system is starting in.
But you were shown the pictures, of course, these pictures of forest and so on, and the seed is have nothing like the tree it growing to, but it needs environment that
it needs an environment.
use,
Exactly.
Its heuristics will be applicable.
Exactly. Yeah. Exactly. Those heuristics are keyed to certain range and types of environments. Yeah. And if you plant it on Mars, it'll never grow. So now, you start to understand a little bit about situatedness and how this all connects together, how intelligence connects to society, the more flexibility you need, the more likely you are to have to guide the system if you want it to evolve at a certain pace. Of course, if a system lives for hundreds of years, then okay, if it takes 100 years to develop a sense of color perception, that's fine. You know, it has several more 100 years to live, and if you can wait that long, so it has to do with the kind of processor that the system has. You know, whether it's how much is parallelizable in it, and for example, with AERA, we didn't really have a clear idea of how many cores we needed. Turns out, for this scenario that we used to test it, we got away with 4 cores on a single CPU on a laptop. I was going to tell you that at the end because it makes the whole thing much more impressive, actually. Or at least it surprised me significantly because we had a system with 64 cores waiting in case we needed it. But we will use it, of course, for more complex things. So it's nice that either we could increase the pipeline of sensory data, or we could make the tasks more complex or take longer, etc. With artificial cognitive systems, you can do all sorts of stretching the various dimensions. So, all right, folks, that's it for now. Have a good weekend. I'll see you on Monday.